Stated Clearly presents What is an atom and how do we know? Atoms are the fundamental building blocks of chemistry. Just like baked goods are made of a collection of different types of ingredients, matter itself is made of a collection of different types of atoms. Scientists have discovered 118 kinds of atoms, which we call elements. You can find them laid out on a chart called the periodic table. All things from the screen this video is displayed on to the eyeballs with which you're watching it are made of atoms, but a single atom is so small it is impossible to see with the naked eye. So there you have it. A random voice from a video you found on the internet claims that everything is made from invisibly small atoms. You may now blindly accept this as fact and happily move on with your day, right? No? Now you are extra curious? You want to know for yourself exactly why it is that scientists think they know that atoms exist? Well, to find out we must travel back in time to ancient Greece. Meet Democritus, the man that many historians credit for first clearly proposing the idea of an atom. In his day, it was thought by some that if you were to chop up a piece of matter, an apple for instance, you could just keep on chopping forever and ever. There was no end to smallness. For reasons not fully agreed upon by historians, this concept did not sit well with Democritus. Instead, he insisted that at some point, you would reach particles so small and so indestructible they could not be divided any further. He called them atomos, or atoms, which means uncuttable. Now, Democritus didn't actually have any evidence to back up his claim, and because of that, many people simply rejected it. After all, that which can be asserted without evidence can also be dismissed without evidence. Let's fast forward several hundred years and hop on over to the Arabic world. You probably know that salt can be extracted from seawater by simply letting it evaporate or boiling it dry. People have been doing this forever, but alchemist Jabir ibn Hayyan and those that followed his work took the science of extraction to a whole new level. Through careful experimentation, they developed complex processes of filtration, boiling, vapor collection, and cooling. They found that crude starting materials could be divided into multiple incredibly pure substances. Pure meaning they appeared to be consistent all the way through, unlike the complex mixtures of matter often found in nature. In the 1700s, a French husband and wife scientific duo, Marianne Poltz and Antoine Lavoisier, studied and built upon the work of their Arabic predecessors. They found that certain pure substances could be broken down even further through chemical reactions. Water, for example, can be boiled into steam, which is still water, but it can also be split into two pure gases, hydrogen and oxygen. No matter how hard the couple tried, however, they could not reduce oxygen or hydrogen into simpler gases. They concluded that the gases must be elements, foundational substances that cannot be created by mixing other chemicals together and cannot be broken down any further. With this concept in mind, scientists everywhere began searching for and listing as many elements as they could, eventually discovering all 118 listed on the modern periodic table. Some, such as oxygen and hydrogen, are gases at room temperature. Others are solids, such as elemental carbon and gold. Others still are liquid at room temperature, mercury and bromine. It was also found that under the right conditions, pressure and temperature, certain elements will react with each other upon mixing to form new substances with new properties. These are called compounds. The elements oxygen and iron can react to form a brown powder known as rust. Oxygen and mercury react to form a toxic orange powder. Oxygen and hydrogen react to form a clear, refreshing liquid. You probably know it as water. Though the steps may be complicated, all of these reactions can be reversed. Elements can be re-separated, and the amount of each element we get back after separation is always exactly equal to the amount that had reacted to form the compound in the first place. Wonderful. Elements are real, and they appear to be essentially indestructible, but what are they made of? If you were to zoom in on one, a chunk of pure gold for example, Can you just keep zooming in forever and ever, seeing nothing but pure gold for infinity? In the early 1800s, a school teacher from England named John Dalton grew fascinated with chemistry. Along with conducting several experiments of his own, he read about every experiment he possibly could, paying special attention to the quantities of each element used up in every chemical reaction. In these numbers, he was surprised to find a pattern emerge. When two elements can react to form multiple types of compounds, they always do so in small, whole number ratios. In this example here, we see that in order to transform a gram of carbon into pure carbon monoxide, we need to add 1.33 grams of oxygen. To turn a gram of carbon into pure carbon dioxide, we need to add exactly twice as much oxygen. That's 2.66 grams. This, and many other similar observations, strongly suggest that oxygen and other elements are made of tiny, indivisible units. Atoms. He didn't know exactly how small an atom was, but the numbers suggested that the atoms of a single element were all nearly identical in size to each other, but different in size to the atoms found in other elements. In 1808, he wrote a 560-page book that briefly mentioned his discovery. It even came with some quite beautiful drawings. While scientists weren't fully convinced that atoms were real, they did find the concept of atoms extremely useful. It helped them make accurate predictions and perform cleaner chemical reactions. In 1905, Albert Einstein, hold on there, in 1905 he was quite a bit younger than that. There we go. In 1905, Albert Einstein proposed an experiment and produced an equation that could be used not only to confirm the existence of atoms, but to determine exactly how big they are. A few years later, French physicist Jean Perrin, or I guess in French that would be something a little more like Jean Perrin, used Einstein's concept to actually do the experiments confirming beyond reasonable doubt, at least to other physicists and mathematicians, that atoms do, in fact, exist. Now, if you happen to love math and possess an in-depth understanding of physics, then great. You can just turn off this video right now and go read his book. But for the rest of us, a little visual confirmation that atoms actually do exist would be nice, right? Unfortunately, individual atoms are far too small to be seen with normal light. The wavelength of light is just too great. This means that normal microscopes cannot see atoms. In the 70s, a group of engineers led by Gerd Bennig and Heinrich Rohrer began working on what they called the scanning tunneling microscope, a microscope they hoped would let us take undistorted images of many different types of atoms. It uses a process called electron tunneling to scan and essentially feel the surface of the sample, much like you can feel around in the dark to get a picture of your surroundings. This is an actual scan of silicon atoms forming the surface of a crystal. The colors here are artificial, but this is real data showing the actual pattern of silicon atoms arranged in the sample. Later work by Dr. Wilson Ho improved the technique and cleaned up the presentation of data. While, quote, feeling the atoms does give us good information, researchers still wanted more. A group led by Dr. Ara Apkarian of the National Science Foundation's Castle Research Center discovered a way to use actual light to see atoms. In the past, this was thought to be impossible because the wavelength of light is so much larger than an atom, but by shooting light at the tip of a probe in a modified scanning tunneling microscope, they were able to essentially shrink the light's wavelength and get it to scatter off the sample onto a detection screen. By moving the sample bit by bit, hitting it with light again each time, they were able to piece together this image of a single nitrogen atom, each pixel representing an individual data point from the scan. If we smooth it out, sharpen the edges, and change their chosen color scheme, it is shocking to find how close John Dalton's old drawings actually were to reality. Our species has finally done it. Over 2,000 years after Democritus first proposed the idea of an atom, we have now received direct visual confirmation. Atoms exist. So in summary, what is an atom? Atoms are the fundamental building blocks of chemistry. How do we know they exist? Through chemical reactions, we can witness their effects. Through mathematical equations combined with indirect observations, we can calculate their various sizes. And finally, with the aid of new technologies such as the scanning tunneling microscope, atoms can now be seen. While the word atom technically means uncuttable, we'll see in the next animation that atoms actually can be split apart. Atoms themselves are made of smaller pieces. I'm John Perry, and that's how we know that atoms exist, stated clearly. Well, folks, there we have it. That was the first animation in my 4-part series on the basics of chemistry, the fundamentals of chemistry. Hope you enjoyed it. If you did, subscribe to this YouTube channel and click the little bell icon. That makes sure that you'll see the next animation when it comes out. Again, there's 3 more to go still, so make sure you're subscribed. This animation was funded in part by the CASTLE Research Center. CASTLE, that stands for Chemistry at the Space-Time Limit. This is a research group over at the University of California, Irvine, that does atomic and molecular imaging. They take pictures of atoms and molecules. When they're not busy taking pictures of atoms and molecules, they do science outreach. They fund projects like this animation that you just watched. And they also produced recently a video game called Bond Breaker that is absolutely wonderful. It will teach you the basics of chemistry and a little bit of nuclear physics. It's totally free to use, to play, to download. You can use it on your phone, you can use it on your computer, you can use it on your tablet. So go check that out as well. There is a link down in the video description. This animation was also funded in part by my patrons over on patreon.com/stated clearly. If you would like to join these wonderful people right here in supporting this YouTube channel, I would greatly appreciate that. These folks are awesome. So long for now. Stay curious.